or the main benefit of using cam follower system is that you can move the conveyor belt as per your requirement. You can stop it whenever you want for some time, and then you can move it again. And also, not only that, you can also control the motion. For example, if you want the motion to follow the path, or motion to follow a certain function, you can also make that possible in case of a cam follower. So we'll also discuss about that. So assembly plants of fast moving consumer goods. So assembly plants are basically conveyor belts that we that cam follower system can be utilized at. And then the pros and cons of cam follower systems relative to the 4-bar linkages is, it is easier to design because it has fewer parts. It only has cam and a follower. And but on the other hand, it is difficult and expensive to manufacture because of the tools that are required to manufacture. It is compact. Again, this is the benefit. And then it is more feasible in critical path motion application. So we'll be formally defining critical path motion as we move on. But for now, just remember that critical path motion applications are those motions in which we want to have a better control over the motion profile or path profile of the mechanism. For example, if we want the mechanism to move in a certain way, in cam follower system, we can control that by defining a function. That function can be a sinusoidal function, or a cosine function, or a cycloidal function. So we'll be discussing about these functions also later on today, or maybe in the next class. So we have more, it is more feasible in critical path motion, where we have better control over the path. And then cam follower system, as we already discussed in the last lectures, that it is a degenerate of a 4-bar linkage. So we can use the linkage transformation rules to find an equivalent system of a cam follower system, as we discussed. So in that case, the coupler link is replaced by a half joint. So now you can see here that these are the two examples of a cam follower system. So the first two, the cam follower system on the top, let's discuss about it first. So you can see a cam here. Sorry, I don't know. Just give me a second. I think I just need to. Why it's not writing here? Anyways, okay. So now in the first two, in the top figure, you can see that we have an oscillating cam follower system. Now, why is it called an oscillating cam follower? Because you can see that we have a cam on the left hand side, and on the right side we have a follower that is connected to a spring. Now, when the cam moves, the follower also rotates, but it cannot have full rotation. Why? Because as it rotates, the spring compresses and it is forced to move back. So the follower in this case is performing to and fro motion, as you can see, as is specified by this omega that is moving. As you can see, specified by the direction of omega, which is moving to and fro. So this type of cam follower is called an oscillating cam follower. And now you can see the 4-bar equivalence of this cam follower on the figure towards your right. So you can see that now the half joint is replaced by a dotted coupler. So this dotted 4-bar linkage and this cam follower are equivalent to each other. And we have already discussed that how we can convert a 4-bar linkage to a cam follower using a half joint and linkage transformation in early during the lecture. So this is again, you can see that cam follower is an equivalent 4-bar linkage. Now, if you look at the bottom two figures, you will see that in this case, the follower is not moving, is not oscillating, but it is moving to and fro, just like a slider. So now you can see that the slider velocity is given by, or the follower velocity is given by V follower, because it is moving to and fro, right? And then this is equivalent to a 4-bar slider crank mechanism. Now, there is a difference between the two. When the cam follower is oscillating, it is equivalent to a 4-bar pin joint mechanism. And if the follower is moving to and fro, in that case, it is, or translating, in other words, it is equivalent to a 4-bar slider crank equivalent, as you can see over here, right? So if you have any question, you can stop me. Okay, now so based on this, we can have the following class. Yes, please.
सर थोड़ा रिपीट कर सकते हैं पिछले वाला कि आपने बताया कि वो ऑसिलेट कर रहा है.
हाँ, इसमें असल में मेरा पेन जो है ना वो नहीं चल रहा असल में. मैं वरना आपको ड्रॉ करके दिखा देता. आई डोंट नो व्हाई दिस पेन इज नॉट वर्किंग. शुड बी वर्किंग एक्चुअली. लेट मी सी. Okay. Okay, the pen is not working. Okay. So you can see here that in this case, this is the follower, right? So if you look at the follower here, what is happening to the follower when the cam rotates with angular velocity of omega as shown by the direction here? So the follower will also move, right? But the follower in this case will be performing to and fro motion, since it is pivoted at this point and it is restricted to move by this spring. So what is going to happen, this when this cam rotates in the direction as specified with this by this omega, the follower will perform to and fro motion, right? So since the follower is oscillating, performing to and fro motion, this type of cam follower is called oscillating cam follower. But if you look at this cam follower, you will see that now this the same cam is attached to a follower, which in this case is translating. It can move to and fro along x-axis, which is defined over here. So since it can move along x-axis, translating, moving to and fro, that is why this type of cam follower is called a translating cam follower, based on the motion of the follower. Is it clear?
Yes, sir.
Okay, now so we can classify the cam based on the cam follower based on the following categories. So we can classify it based on the type of follower motion, as we saw in the last slide. So we can have translating follower motion, or we can have rotating or oscillating follower motion. Again, we can also classify the cams based on the type of cam. So we can have a radial cam, we can have a cylindrical cam, we can have a three-dimensional cam. Then we can also classify the cams based on the type of joint closure. For example, it is whether it is forced close or it is form closed. So can you guys tell me in the previous slide, is this an example of form closed or forced closed? Anyone?
Force close.
Yes, it is an example of force closed. The form closed we discussed, it is the pin joint is an example of that. In this case, these two cam and the follower are held together by force. So this is an example of a force closed cam. Now, then we can also classify the cam followers based on the type of followers. The follower can be a curved follower, a flat follower, a rolling follower, and a sliding follower. So an example of a rolling follower is shown over here. So this is an example of a rolling follower where we have a rolling follower. Now in the next slide, we'll also see other examples of follower also. The follower can be curved, flat, rolling, and sliding. Now cam followers can also be classified based on the type of motion constraints. There are two types of motion constraints that we will be talking about in this chapter. The first one is critical extreme position, which is also abbreviated as CEP. In this type of motion constraint, we only know the initial and the final position of the cam follower. How we define the path, that is up to the designer to choose. And in critical path motion applications, we not only know the initial and the final position, but we also know the path or the path function that the cam follower will be following, right? It is possible that the whole path is defined for us, or we only know specific path or specific function, that how the follower is going to move. The rest we can choose. So when we have critical path motion, the path is also defined. And then the last type of classification is based on the type of motion program. So whether we have rise fall, we have rise fall dwell, or we have rise dwell fall dwell. Now we'll discuss about this motion program also. Rise, what does rise mean? What does fall mean? Dwell, what does dwell means? We will be discussing about this in the coming slides also. So this is the CAM terminologies, or in other words, the classification of CAMs. Now we already discussed about this, that this is the first two examples above shown in the figure above are for oscillating cam follower, and the ones that are shown below are for the translating cam follower. In this case, the classification is based on the motion of the follower, whether it is oscillating or it is translating. Now in this figure, you can see that cam follower is classified based on the type of the follower that is being used. So now you can see here that this is an example of a roll follower. We have a roller follower here, and then this is an example of a mushroom follower. You can see that the shape of the follower at this end where it is connected to the cam is just like a mushroom, and then this is an example of a flat faced follower. So we have the classification based on the follower. Okay, now another thing you can see in all the three cases, you can see that the follower is translating, moving with velocity v follower, whereas the cam is rotating with omega cam. So the cam is rotating at this center point, whereas the follower is translating. So this is an example of a translating cam follower also. Now, critical extreme position. So it is also abbreviated as CEP. So design specifications define start and finish positions of the follower. So when we are asked to design a cam follower based on critical extreme position, the design specifications will normally include the start and finish position of the follower. They do not specify any constraints on the path motion between the extreme positions. So you can select whatever function you want between the start and the finish position, right? But now again, we will be discussing that there are certain rules to select the motion profile or path profile of the cam follower. So if our design does not satisfy those rules, then it is a bad design. So based on that, we will classify if it is a good design or a bad design. So we will also be discussing about those paths. And then do not specify any constraints on path motion between extreme positions. It is easier to design because of the freedom to choose the mathematical functions to go from the low dwell position one extreme to the high dwell position. So can anybody tell me what 12 means? We already discussed about 12 at the start of the course. So can anybody tell me what 12 means? Anyone? Any idea what 12 means? So 12 is when the cam and the follower, they do not contact each other. When they do not contact each other, that means the cam is rotating, but it is, since it is not in contact with the follower, so the follower will not be moving in that case. When the follower is stationary, that means we have 12 in that case, right? So can you guys hear me?
Yes, sir.
Yes, sir.
Okay. Okay. So now, so we'll be discussing about 12 later on also. So now the other type of motion constraint that we have is called critical path motion, which is abbreviated as CPM. CPM is more constrained in the sense that the path motion, such as displacement, velocity, and or acceleration values, are defined over all or part of the interval of motion, right? So we also define the path motion either over all or part of the interval of motion as the follower moves. So this is called critical path motion. Now, another type of classification is based on the type of motion program that we have. Motion program means that how the cam follower is going to move. So it can have rise fall. When it is rise and fall, then the number of dwells that we have is zero. Then because then the cam and the follower are not losing contact at any point. That means there is no dwell. And then when we have rise fall, when we have to design a cam follower based on rise fall, it is more convenient to use a 4-bar linkage, as 4-bar linkage does not have any dwell. When we have dwell, then we normally use cam follower system. So we can have two situations in that regard. We can have rise fall and dwell. We'll discuss about rise fall later on. So for now, just remember this thing. It is also called RFD. In this case, the number of dwells is equal to 1. Then we have rise, 12, fall, 12. It is abbreviated as RDFD. In this case, the number of dwells are 2. So it has rise first, followed by a 12, and then fall, followed by a 12, right? So in this case, you can see we have a figure like this. So if we say that we have theta, theta is the rotation or the revolution of the cam, and then on x-axis, and if we plot on y-axis, either we can plot s, which s is the displacement. We can also plot velocity. We can also plot acceleration. And the fourth thing that we can plot is called jerk. Jerk, we will also be defining jerk. For now, remember that we know the if we take derivative of acceleration dA by dt, that will be defined as jerk. So jerk is defined as the derivative of acceleration with respect to time, right? So now if we have a s theta graph like this, so now let's suppose if we have rise first, so rise means we are it is rising, right, like this, right? And then it will be, when it rise, it will be the follower is increasing its displacement. That means it is rising, it is moving along the positive x-axis, for example, or it is rotating in anti-clockwise direction. So it is rising, so it will be represented like this, right? So s means it is not rotating, it is translating. So if it is translating in positive x-axis, this is the rise. So this will be the maximum displacement it will cover. Now if this is done from 0 to 90 degrees, for example, when the cam rotates from 0 to 90 degrees, the follower is increasing its displacement, right? So this is called rise. Now when it is followed by a 12, that means now for example, from 90 to 180 degrees, so there is no increase in displacement, so the displacement is constant. So this is called 12. Now after from 180 to 90, let's suppose from 180 to 270, the follower is moving back to its initial position. So it is called fall, like this, and it moves back to its initial position when the displacement is 0. And then again it is followed by a 12. 12 means that now for the rest from 270 to 360 degrees, the follower is not changing its position, right? It's not increasing its displacement. So this is called R12. So this type of motion profile is, sorry, I didn't understand.
Sir, my apologies, sir. इसमें S क्या चीज है?
This S is the displacement of the follower.
और सर हम अच्छा ठीक, कांस्टेंट डिस्प्लेसमेंट को हम कह रहे हैं 12 ओवर रखने के, वहां पे कोई चेंज नहीं आ रहा
हाँ, देखिए ये आपके पास कैम है, ये आपके पास रोलर लगा हुआ है और आगे आपके पास फॉलोअर है इस तरह का, ठीक है। अब वो कह रहा है जो ये डिस्प्लेसमेंट जो रोटेशन है, ये हम जो एंगल जो चेंज कर रहा है वो कैम चेंज कर रहा है। कैम इज द इनपुट इन दिस केस, राइट। सो दिस थीटा इज रिप्रेजेंटिंग द मोशन और द एंगुलर चेंज ऑफ द कैम, right? And then this S is representing the displacement of the follower, right? So when the cam moves from 0 to 90 degrees, we have rise. Rise means that when this cam rotates from 0 to 90 degrees, the follower moves up and it increases its displacement. Now when the follower is moving up, it can follow a linear motion, it can follow sinusoidal motion, it can follow simple harmonic motion, it can follow cycloidal motion. So there are different motion profiles that this follower can follow, and which one is appropriate or which one is good design, we'll discuss that later on. Yes, please. Any question?
सॉरी सर, वो गलती से माइक ऑन हो गया था।
Okay, no problem. Okay, so now this is called rise. So on the x-axis we have the displacement of the follower in this case, and on on y-axis we have the displacement of the follower, and on x-axis we have the rotation of the cam, right? So now is it clear now? Okay, so now let's suppose if we have only one rise. In the second case, we have rise, fall, and 12. So in that case, we will not have this 12. This 12 will not be there. We will have rise followed by a fall, and then we will have 12. And in the first case, when we don't have any 12, in that case, we will only have rise and 12. So it will only be like this. We have rise and then 12 like this, right? So these are the three types of motion programs that we will be discussing about. Now the SVAJ diagram. So I already showed you the SVAJ diagram in the last slide. So SVAJ stands for, S stands for displacement, V stands for velocity, A stands for acceleration, and J stands for jerk. So when there is sudden change in acceleration with respect to time, then we feel that jerk, right? So we define jerk as dA by dt. Now the main objective of the so before I discuss the objective, this is the so I'll discuss the objective first and then let's discuss about that. The main objective is to select the mathematical function of displacement, velocity, or acceleration to define the motion of the follower. The easiest approach is to linearize the cam. That is, we assume the linear displacement function. Now, what are the advantages or disadvantages of linear displacement function? We will discuss in the coming slides. And then then we assume the linear displacement function, and then we analyze the SVAJ diagram, right? So what are SVAJ diagram? For SVAJ diagram, so there's a typo here. This is y-axis. This is y-axis, and this should be x-axis. Sorry, this should be x-axis. This, right? So now, and the SVAJ diagrams are on your y-axis. You have either displacement, velocity, acceleration, or jerk, and on your y-axis, on your x-axis, you have the camshaft angle, as we saw. You can also have time t, or you can have theta. Theta is mathematically defined as omega into t, where omega is the angular velocity. We know that omega is theta by t. So if, in other words, if we know omega, we can work out this also with respect to time. So theta in that case will be omega t. So on our y-axis, we have S, V, A, or J. On x-axis, we have theta. So this is called SVAJ diagram. So now this is just an example of what we discussed. So now you can see that this is an example of an SVAJ versus theta diagram. On or your y-axis, you have displacement in millimeter of the follower. On x-axis, we have the angular displacement theta of the cam. Now you can see that initially from 0 to 60 degrees, we have cycloid rise. Cycloid is a function that is used, a mathematical function to define the motion. We'll be discussing about these mathematical functions later on when we define these mathematical functions. For now, just remember that cycloid is a non-linear function. And cycloid rise means that from 0 to 60 degrees, the displacement of the follower is increasing. So this is the maximum displacement. So the maximum displacement is, in this case, is 25 mm. Right now, so that means a function used is cycloid rise. Start angle is 0 degrees, end angle is 60 degrees. Now, what is delta angle? Delta angle is the difference between the end angle and start angle, that is 60 minus 0. So in this case, it will be 60 degrees. Now, in the next part, you can see that from 60 degrees to 90 degrees, if you look at the x-axis, from 60 degrees to 90 degrees, we have 12. 12 means that the displacement of the follower remains constant, 25 degrees from 60 degrees to 90 degrees. The function used in this case is called 12, and then the start is 60 and the end is 90. So the delta angle in this case will be 90 minus 60, which is 30 in this case, right? Now, in the next slide, you can see that we have a fall function. Then we have a fall function from 90 degrees to 150 degrees. So from 90 degrees to 150 degrees, we have fall function, which is modeled as mod sine for fall. And then the delta angle in this case will be 150 minus 90, which is 60 degrees in this case. So these functions that are used, we will be talking about these functions mathematically in detail also. For now, just remember that they are rise and fall, and then categorized or classified by different functions. Then after that, you can see that from 150 to 180, we have 12 again, where the displacement remains 0. When we had fall, at the end time, the displacement became 0. Now the displacement remains 0 from 150 to 180. So that is called 12. And again, if we subtract the start angle from the end angle, that will give us the delta angle, which is 30 in this case, right? So we will be going from 0 to 360 to see when the cam rotates to a total of 360 degrees, how is the follower moving. So this will give us the diagram of S displacement versus theta. So again, after that, we have fall again. Sorry, this is rise actually. So this is a typo here. This is rise. This should be rise. So we have rise again from 0 to 25, and then it is from 180 degrees to 240 degrees. So delta angle in this case is 60. Now we have gone from 0 to 240, and we have different segments or intervals where we have rise followed by 12 and then followed by fall. So you can see that we have different types of motion characteristics throughout the motion of the cam. So now again, after that rise, we have 12 for 30 degrees. And then after this rise, I'll just quickly go through this now. After 12, we have another fall. And then this fall is modeled as a simple harmonic motion fall, right? And it happens from 270 to 330 degrees, where the delta angle is 60 degrees. And this fall is followed by a 12 again from 330 to 360 degrees. So this completes the 360 degree revolution of the cam. Now, if we combine all these graphs together in a single graph, that will give us the motion profile of the displacement profile of the follower when the cam rotates from 0 to 360 degrees. So you can see here that on your x-axis we have the cam angle. Now it is changing from 0 to 360 degrees, and on your y-axis you have the displacement. Now you can see that first we have rise, then dwell, fall, dwell, rise, dwell, fall, and then dwell. So the motion profile that we saw individually in the last few slides, we combined them together, and this is the displacement versus cam angle that we have. Now, this is just a summary of what we have done. He has combined all the segments or the functions used in a single table, and also listing the start angle, end angle, and delta angle. So we go from 0 to 360. So now can anybody tell me, if we have displacement versus cam angle diagram, is it possible to get the velocity versus theta diagram from here? Can we get it? Anyone?
Sir, इसकी slope से
Yes, normally these cycloid rise, mod, sine, fall, we will have mathematical functions of that. When we design a cam, we select a mathematical function based on these functions used. So if we have a mathematical function for displacement, right, as a function of time, we can simply what we can do, if we differentiate it with respect to time, if we have displacement, if we differentiate displacement with respect to time, that will give us velocity, right? So we can simply get velocity by differentiating this function with respect to time, and then we put the angle from 0 to 90 and so on, and then we get the values. We know that theta is also given as omega t. So theta, when we say theta, theta is also giving us change with respect to time also, right? So if we change theta in this equation, that will also give us, we can calculate the velocity by differentiating displacement with respect to time. Similarly, if we have the velocity, we can differentiate velocity with respect to time, and that will give us the acceleration. And similarly, if we have acceleration, if we differentiate acceleration with respect to time, that will give us the jerk. Now in the next slide, so this is just an introduction where he's telling you how we can, what is SVAJ diagram, how do we calculate them. We will also do some examples on this using real mathematical functions, and then we will calculate it. That will be, and then it will be more clear to you. But for now, this is just an introduction, so to tell you how we get these diagrams. So now in the next slide, we have velocity versus cam angle. So now how he has calculated this velocity in a similar manner. We know the mathematical function of cycloid rise. We differentiated with respect to time. We put the angles inside it, and we get a velocity profile like this. Now you can see that the velocity profile is starting from 0. It is reaching its peak at around 45 meter per second, and then it falls again and it becomes 0 over here. Then it is followed by a 12, because 12 is a straight line. 0, there is no, it is constant. So the velocity here will also be constant, that is 0. So when we have 12, you can see that there is no change in velocity. Then we have a mod sine fall. This fall is characterized by this function, and then you can see that we have a peak over here, and then it falls again, and then again we have a 12 where the velocity remains constant. Again, we have a rise, which is characterized by this peak, and then we have dwell, fall, and dwell. So this is the velocity profile that we get from the functions of the displacement that we used. Is it clear so far? Okay, so now again, now if we want to get the acceleration from here, we can again differentiate velocity function with respect to time, and that will give us the acceleration. Now you can see that this is the acceleration versus cam angle diagram. So now you can see that in this case, the acceleration is increasing first, reaching its peak, decreasing, reaching its lowest value, and then going back to the initial position, and then followed by a 12, followed by a fall, and then 12 rise, 12, and then fall and 12. So this is the profile, velocity profile that we get. acceleration profile. Now, if I want, this is a question for you. So if you look at this profile, do you think it is a good profile or not? Anyone?
Not a good profile.
Pardon?
Not a good profile.
Why?
इसमें बहुत extreme changes हैं acceleration के that can exert considerable stress on the material of cam and the follower.
Yes. So one of the thing here is that the velocities, you can see that the velocity is going very high, then decreases, and then goes very low and decreases. So that will put a lot of wear and tear on the cam follower, right? But again, there is no abrupt change in the velocity. If you look at here, the velocity first increases, then decreases and becomes zero over here, and then it remains zero and then increases again. So there is no abrupt change in the velocity, although the peak values are very high, which will put a lot of stress on the cam follower, and it is subject to wear and tear. But at the junction between the rise 12 or the fall 12, you can see that there is smooth change in those parameters. So the velocity is changing smoothly at the junctions, or at the junction point between the rise 12 or the fall 12, right? Similarly, if you look at the displacement function, you can see that again in this case also there is no sudden change over here. There is no sudden change at the points where we have rise 12 or fall 12. But if you look at the velocity, if you look at the acceleration profile now, you can see that at this point the acceleration becomes zero, and it suddenly changes to 270 degrees, right? So there is a discontinuous change in the acceleration at this point, so which is unacceptable. So this is unacceptable. So we need to have a continuous or a smooth change in the velocity, displacement, velocity, and acceleration. If there are discontinuous changes or sudden changes in the displacement, velocity, and acceleration, that means that the design of the cam follower is not good. So this comes down to the fact that we need to select the appropriate functions of the cam for velocity, for displacement, velocity, and acceleration, so that we can have a good design. So we'll discuss about that also. Now if we take derivative of acceleration with respect to time, so you will see that will give us the jerk. So now in case of the jerk, you can see again this is not a good design. Why? Because at these 2 points where we have sudden change in the acceleration, what will be the value of jerk here? Can anybody tell me? Here dt is approaching zero, right? So what will be the value of jerk at these 2 points of acceleration? It will be infinity, right? So because the time change is very small, so the jerk that we are going to have at these 2 points will be infinity, which again is not acceptable. So we cannot have infinity for any of the SVAJ diagrams, right? So this is also not an acceptable design. Any question? So the yes, please.
तो ये इस ग्राफ में जेड को जो डिस्प्ले किया है तो इन्फिनिटी वाला किस तरह होगा उसने नहीं किया उसमें
सॉरी, मुझे आपकी आवाज क्लियर नहीं आ रही।
तो आप कह रहे थे 2 पॉइंट से जहाँ पे इन्फिनिटी आ जाएगी जेड
हाँ, ये
वो
इसमें सही तरह
इस वाले
शो
ग्राफ
नहीं किया हुआ। यहाँ इन्फिनिटी आना चाहिए, इस पॉइंट पे और इस पॉइंट पे वी शुड हैव इन्फिनिटी हियर। ठीक है, so I think there's a typo here. These 2 points should have infinity actually, because there, if we differentiate this should be giving us infinity results over here for the jerk. So this is a typo here, right? So just make note of this. And also jerk, the units of jerk, because it is acceleration divided by time, so the units will be millimeter per second cube in this case, right? So now this is called SVAJ diagram. So we have already discussed some of the points that are useful in designing a good cam follower. One, there should not be any discontinuity in the SVAJ when we design CAM, there should not be any points where we have infinite values of these parameters. Number three, the peak values of there should not the peak values of the displacement, velocity, acceleration should not be very high. So these are the three parameters that we already saw from this design. So we'll be discussing them also later on also. So now this is the same diagram which is being shown as combined together in one. This is called SVAJ diagram. Again, there is a typo here. I'm sorry about that. So this should be displacement actually. This is displacement. The next one is velocity. The next one is acceleration. And this one is jerk here. So we have SVAJ diagram over here. So this is called SVAJ diagram. Now, this is also called CAM timings. SVAJ diagrams are also called CAM timing diagrams. Now, this is again the same, he's showing you the same thing, but now a simplified one. So now you can see here that he has divided the x-axis, which is the CAM angle, into four different regions or intervals, right? So now from 0 to 90, it is called low 12. When we have 12, so this is called low 12 at the start. Then this is followed by a rise from 90 to 180 degrees. So now if you look at this rise, what type of function do we have for this rise? Anyone? This is a linear function, right? So now we have displacement on our y-axis and a CAM angle on our x-axis. The first motion profile from 0 to 90 is 12, low 12, and then it is followed by a rise 90 to 180 degrees. Then again we have a 12. This is called a high 12 now. So now you make note of the low 12 and high 12. Low 12 is when we have displacement, low displacement, and high 12 is that when we have high constant displacement. And this is followed by a fall like this. Now, in this case, the rise and the fall are modeled as a linear function. Now, so we'll just quickly cover this start and then we'll finish in 5 minutes today. So now, if we go to first example, so that is called a double 12 cam design. So why double 12? Because we have low 12 and we have high 12. So this is again we will see that this is a naive chemical cam design, which is a bad cam. And why bad cam? We'll be discussing the SVAJ diagrams the same way as we discussed the last one. We'll see the peaks, we'll see the discontinuities, we will see if we have infinite values for some parameters, and then based on that we will deduce whether it is a good CAM design or a bad CAM design, right? So the problem statement that you will be given in the exam for such questions will be specified a 12 at zero displacement for 90 degrees. This is called low 12. So from 0 to 90 it is low 12, which is zero displacement. Then we have rise of 1 inch 25 mm in 90 degrees. Normally you will be specified a function, whether it will be simple harmonic 12 or it will be linear. In this case we are assuming it to be a linear function. So it is going linear. If the displacement is increasing linearly from 0 to 25 mm in 90 degrees. That means initially if 12 was from 0 to 90, then from 90 to 180 it is going to be rise. So this 90 is delta angle, right? And then at 3 we have a 12 again for delta angle of 90 degrees. So that means from 180 to 270 we have 12, and the displacement remains constant at 25 mm, and then that is followed by a fall of 1 inch. That means the displacement is going from 1 to 0 again, from 270 to 360 degrees, and this is called 12. This is called fall. And then the CAM angle omega is given as 2 pi radians per second, or in other words we can also convert it into revolutions per second, RPM, which is 1 revolution per second. We know that omega is 2 pi n by 60, where n is the number of revolutions. So we can also calculate it from here. So now this is the displacement versus theta diagram we already discussed. So you can see we have 12, low 12, rise, linear, high 12, and fall, right? Now, if we want to calculate the velocity from here, what we can simply do, we can differentiate s by ds by dt, and that will give us the velocity. Now, if we calculate the velocity, if we differentiate, the order of differentiation reduces or increases? The power increases or decreases? Anyone?
Increases.
It decreases, right? Differentiation means the power, the order, the higher order becomes lower order by 1, right? The power decreases by 1, right? So now if you look at here, you will see that if we have a velocity versus theta diagram, you will see that the 12 is 0. Now because the order decreases, so you can see that this is the velocity profile that we get. The velocity increases initially, it becomes constant, and then it decreases again. This is high 12, and then again we have increase in decrease in velocity, increase in velocity in negative direction, and then constant velocity, and it decreases back to 0. So this is the velocity diagram that we have. So do you think this velocity diagram is acceptable or not?
Not acceptable.
Not acceptable. Why? Because of the discontinuities, right? So we'll just wind it up here, and then we'll resume our discussion on this in the next lecture next week. Okay. So thank you very much for your time. So I'll just take the attendance and then let you go.
सर मेरा एक क्वेश्चन है आखिरी 5 मिनट का बस।
जी जी।
सर जी मुझे समझ नहीं आ रहा कि आप ग्राफ का पूछ रहे हैं कि एक्सेप्टेबल और नॉट, और वो मुझे समझ नहीं आ रहा कि आप कैसे उसको एक्सेप्टेबल कह रहे हैं और नॉट एक्सेप्टेबल।